All right, everyone. Welcome to one of the very first TWIML Democast. This is a little experiment we're running where, in addition to me and a wonderful guest, in this case, Luke Marsden, CEO and founder of Dotscience, we've got a demo that you can catch. If you're listening to this via the podcast, I encourage you to jump over to YouTube. You can find this at TWIMLAI.com/democast/dotscience. Feel free to continue on audio only, but this conversation will be enriched by a demo that we'll be jumping into. Before we get too much further, Luke, welcome to the TWIML Democast. I don't know why
Hey, Sam, thanks.
over this,
Thanks.
this name here. I got to get used to it.
Yeah, thanks so much for having me on.
Awesome. So, let's get started having you introduce yourself to the audience. Tell us a little bit about your background and how you started working at the confluence of MLOps, DevOps, and machine learning.
Absolutely. So, hi, everyone. My name's Luke Marsden. I'm the founder and CEO of this little company called Dotscience. We are working on MLOps and making it easy for data scientists to deploy and monitor machine learning models on Kubernetes. I guess my background is very much, I've come from the DevOps space, as have many of the people on the team. And I was deeply involved in the early days of Docker and Kubernetes, where my former startup, Cluster HQ, built the first data layer for containers, so connecting Docker containers to persistent storage, for example. And so I'm coming at the world of AI and machine learning, and we all are, we're coming at the world of AI and machine learning very much from a DevOps background. And what we found is that a lot of the things that software developers take for granted in terms of the tooling and the workflows that they have, which enable controlled collaboration and continuous integration and continuous deployment, those tools and processes aren't as mature in the world of machine learning. And so we see a lot of chaotic practices around like emailing and slacking Jupyter notebooks to each other, manually keeping track of metrics and hyperparameters, and basically failing to have reproducibility and provenance in the same way that people take for granted in software engineering. And the reason for that is that machine learning is fundamentally harder than software engineering. So that's where we're coming from, and that's what we built the Dotscience platform to solve.
Nice. I'm curious, when you say machine learning is harder than software engineering, I'm curious what that means to you. I imagine that not many people listening to this show will disagree with that. But I'm curious why you say that.
Yeah, sure. And actually, if you don't mind, I'll pull up a slide that I used to describe that problem in particular. And what I mean by that is that in the software development lifecycle, we have this code, test, deploy, and monitor process. Yep. And that, of course, has its complexities and its subtleties, but fundamentally, that is what software development and DevOps with software is about. But when you start thinking about models as software, and when you think about machine learning models as deployable artifacts, then you realize that there's more complexity in that space because there's data and there's models, as well as the software which trains the models. And when you've trained a model, then you get metrics coming out of the model as well. And so you've got lots more moving parts, basically. You need to be able to keep track of the data, which version of the data set you trained the model on. You need to keep track of which parameters you use to train the model. And all of these go into what we call data runs and model runs. So data run is where you're tracking the relationship between some input data and an intermediate data set. So for example, you're taking raw data and you're turning it into a training, test, and validation set for training a model. And then what we call model runs are where you are training a machine learning model on a certain data set, maybe that intermediate data set that was the output of the last step. And and then you're creating a model, and it's that artifact that's deployed into production and then monitored. And it's more complicated. There's more moving parts, and if you're not careful, it's quite easy to get into a mess.
Nice, nice. Before we jump too deep into this and transition into the demo, Dotscience was a founding sponsor for our recent conference, TWIML AI Platforms. Your team, Nick in particular, presented on MLOps generally, but also a manifesto that you guys are evangelizing. Tell us a little bit about this manifesto.
Absolutely, and it was a real privilege to be a founding member at the TWIMLCon. It was a fabulous conference for us. Really, kind of AI platforms is obviously what we do. So it was a really relevant conference for us, and thank you for hosting it. And the manifesto that I'm talking about is on the website here. And it basically says that in order for machine learning as a discipline to be production ready, to be mature, and to get to the same level of sophistication that software engineering and DevOps does, then you need 4 characteristics. It needs to be reproducible, accountable, collaborative, and continuous. By reproducible, I mean that someone else has to be able to come along and reproduce the model that I might have put into production 6 months ago, even if I've left the company, for example. Accountable means that you need to be able to hold the model to account in the same way that you hold humans accountable for their decision making, which at least means knowing who they are, as in which model it is, which version of the model, and on what basis it's making its decisions. And by that I mean which data it was trained on, at least. Collaborative is about being able to collaborate between multiple people without treading on each other's toes. In the same way that GitHub has enabled asynchronous distributed collaboration for software engineering. And continuous is really about being able to deploy a model automatically and then statistically monitor it for drift, and then take that back around into the model development lifecycle again. So that's where we're coming from with the manifesto. And it's proving to be something that's resonating with a lot of people. I was talking to a guy in Japan just this morning who saw the manifesto on Twitter and reached out and wanted to connect. So it's definitely working.
Is there a particular challenge among these 4 that resonate most strongly with people?
I think it depends where people are at in their life cycle. I think that for a lot of people, especially enterprises, they're really just struggling to get models into production at all. Because the whole idea of a model as software can be alien to some organizations, and even then, the barriers to getting those models deployed into production can be significant, just because they're new and different. Organizations are familiar with shipping software, but this is a new world, and so I guess that sort of highlights the continuous aspect of the manifesto, continuous delivery, or at least the ability to ship models at all. There's kind of a blockage there. But then more sophisticated users who have got models into production then find that they're coming across the reproducibility and accountability problems. And as their teams scale up, then collaboration becomes a bigger problem as you have more people involved.
Okay. One of the things that I've written about in kind of talking about the space in particular in the machine learning platforms ebook that we published earlier in the year is there's this, at least I observe, a tension between kind of products and companies that are going after this broad end-to-end machine learning workflow versus offerings that are kind of specializing in a particular niche or step in the workflow that have the luxury of going a lot deeper. I'm curious, do you see that tension as well, and how it manifests itself for you?
Sure. I mean, there's certainly a lot of product to build. when when you're doing the end-to-end life cycle like we
A
are.
lot of expertise to gain and
Yeah,
a lot of use cases to see.
and I think, I mean, that's where Dotscience being open and interoperable comes into play. We have a little spiel about that on our product page here, but I think the key point there is that we're doing everything that you need in the lifecycle well enough that you can just pick up Dotscience and use it out of the box for probably the 80% use case. And because we come from a background of data versioning and provenance tracking, we're really strong on the development side and the reproducibility, data versioning and provenance. The pieces around deploying to production and monitoring in production are newer. But we also have a lot of expertise in the team around Kubernetes and CI and continuous delivery and such. But I guess what I'd say there is that if you need to do something more sophisticated than what we currently support on the deployment or the monitoring side, for example, it's super easy to plug Dotscience into your existing CI system, for example. And so we're announcing a partnership with GitLab in the coming weeks, where we are also going to support building your Docker images in GitLab rather than inside Dotscience. And yeah, that philosophy of not being a walled garden means that, yes, we provide the end-to-end, but also if you want to swap out one of our sort of lightweight built-ins with something more sophisticated, then we're also providing the hooks to do that. So I guess that's how we're tackling the end-to-end depth versus breadth challenge.
Sounds a lot like you're taking a cue from the original Docker motto of batteries included but replaceable.
That's true. And actually, it's funny you mention that, because I was very involved in Cluster HQ in trying to make sure that that was actually true for storage plugins with Docker. And adding the right hooks in at the right time is essential. And I could talk about that for a lot longer than we have time on this podcast.
You mentioned that the core of the company's DNA, at least from a product perspective, is the storage aspect and what that enables from a provenance perspective. Can you drill a little bit deeper into that aspect?
Yeah, sure. I mean, it might actually be a good moment to show you rather than telling you.
Okay.
How about I kick off with the demo? Is that all right?
Yeah, let's
yeah.
do it. Let's
okay, cool. So I'm going to jump straight in here, and I've got two accounts.
And I'll just reiterate for anyone that wants to follow along. This will be up on YouTube. The quickest way to find it will be to go to twimlai.com/democast/Dotscience.
Awesome. Thanks, Sam. Yeah, so I'll dive straight into the demo. What we've got here is we've got two user accounts. We've got the Luke Demo 102 user account here. And then in this other screen here, I've got an account for my imaginary collaborator, Fred. And so bear that in mind when we're looking at these screens, is that Luke's got this, this white Chrome browser, and Fred has got this bright yellow one. So that's kind of easy to follow. It makes it easier to follow along to who's doing what as we go through. So the first thing I'll show you is that we've got some public projects inside Dotscience, and they are kind of like sample projects. So as soon as you go into Dotscience, this is a brand new account. I can go into the road signs end-to-end example, and I can fork this project. And so just by clicking the fork button, it creates that fork. And so what you'll see is this notion of forking is very similar to GitHub's notion of forking. And it does enable this sort of style of collaborative or constructive collaboration.
So what exactly have I forked?
Well, so you forked a project with a complete history of runs, with all of the data sets attached to it in the same way that the data sets were attached to the original one. and any code, data, and metrics that come along with it. Now, the only run in this project actually is the run which uploaded the files originally. So at the moment, this project isn't that interesting, but we'll change that. So the next thing I'm going to do is I'm going to hit this button to start Jupyter. Now, Jupyter, of course, is a very popular tool for doing data science. A lot of data scientists work in Jupyter, which is an IDE basically for doing exploratory data science work, building models, and writing Python primarily. We also support running Dotscience just via the Dotscience Python library. So you can drop it into whatever other development environment you already use, whether it's VS Code or Vim or Emacs or whatever your preference is. But yeah, Jupyter is baked in, and what you can see here is that as soon as I spun up this project, the Jupyter environment was in exactly the same state it was when we published this sample project. So I'm just going to jump straight in here, and what we can see is we've got the Dotscience tab that says the Dotscience is ready and waiting, and if we get started. The first thing we're going to do is do a Dotscience run. And what I mean by a run is that we've imported the Dotscience Python library, and then we tell Dotscience you're running in a Jupyter notebook with the interactive command, and then we start a run, and then we say, well, in this run, we are going to output a file, and this actually is just a file that we happen to upload into Jupyter. It could be a file that we've downloaded from the internet. It could be something that we've slurped in via PySpark or integrated with a versioned S3 bucket by adding an S3 dataset. But in any case, we then do a ds.publish command. And so this is kind of important because ds.publish corresponds to exactly the point at which Dotscience will version things. ds.publish will tell Dotscience, I've done a data run or a model run, please make a record of it. And so the very first thing you can see is that we're recording the existence of this CSV file, which is the labels file. And then if we go to the runs here, we can see that run has been recorded. And the interesting thing about this run is that we've got the provenance information for what that run did. It said this version of this code running created this version of this file. And we also record who did it, when they did it, exactly what environment they did it in, so the version of the libraries and Python and everything. And we're also recording the exact version of the notebook. So you can see the diff between the notebook before and the notebook now is simply the addition of this Dotscience run metadata, which is how Dotscience picked up that run happened. So let's jump back in. I know we don't have very much time to go through all of this, so I'll go fairly quickly. The next run that we're going to do is a conversion. We're going to convert that CSV file into a JSON file, and that's because that's needed for one of the later steps. And so let's look at the provenance for this. Well, the provenance for this is slightly more interesting now, because we can see that it's kind of joined up. This version of this JSON file came from running this run in this notebook, which read in as input this CSV file, and that CSV file came from this run. And so we're kind of building up this map of what's happened to get us to the current state. And it turns out that this provenance graph, or this sort of map of the history, the lineage of all of the assets in the project, is super useful when you come back to try and figure out what happened later. Like this machine learning model that's making decisions in production, exactly which data was it trained on? You'll always be able to tell exactly the answer to that question.
And do you only get that if you're running your pipeline in a single notebook, or if you've got multiple users in a collaborative environment, working on separate steps in the pipeline? are you still able to get that comprehensive view of Provenance?
Yeah, you're still able to get the comprehensive view of provenance, even if it's multiple people doing different steps. And you can also get that view of provenance when some of the steps happen in Jupyter, and some of the steps happen via executing a Python script through one of our pipelines.
Okay.
So I haven't included the pipelining feature in this demo, but we can maybe do that in a follow-up or something. So this final run is downloading some data from the internet, and so we can see the provenance graph of this one. And so this is reading in this. Well, it's downloading the data from the internet, and then it's spitting out a test.pickle, train.pickle, and a validation set.pickle file. And those data sets are going to be used later in the example. So I'm now going to go ahead and train a road signs model. So the data that I downloaded is a bunch of German road signs. And what we're going to do today is we're going to build a Keras model in TensorFlow that is able to classify pictures of road signs. And you can imagine that that would be useful in an autonomous vehicle, for example. So I'm going to start out.
That the tool itself is agnostic to the particular choice of framework.
Yes, exactly. So Dotscience will work with any data engineering libraries. It will work with any machine learning libraries. The only limitation at the moment is that the deployment and monitoring piece, which is turning a model into a Docker image and deploying it to production, that currently only works with TensorFlow, but we're working on scikit-learn support right now. And then we're going to add support for other ones as we get demand from customers to do that.
Okay.
So
I've got some questions there, but I'll let you finish this first.
No, it's fine. This is a good time to ask questions, actually, because doing this image pre-processing here takes a minute or two.
Oh, well, I'm curious about, besides from your history with Docker and the team's familiarity with that approach. There are lots of different ways that folks go about kind of packaging up models for deployment. Why the choice of doing that inside of a container?
Well, I think that Docker containers have pretty much become the de facto way to package up machine learning models. At least that's what I've seen. The benefit of containerization is that you can create a machine learning model and build it into a Docker image, and then you're absolutely guaranteed to know that exact image with all of its exact dependencies and all of and the model data it's immutable at that point. It's frozen. And that means that if that model gets deployed into production today, it will behave in exactly the same way that if it's deployed into production in 6 months. And it doesn't depend on the version of like the Python libraries on your server at any one point in time. And also that immutability is important for reproducibility, because it means that if you've got a model running in production, you'll be able to trace back from the tag on the Docker image to the exact provenance in Dotscience. And so, using Docker in that way is a good fit for what we're trying to do in terms of reproducibility and bringing these DevOps principles to bear in machine learning.
And so does that container that you create include some type of runtime scaffolding that exposes your model as a service, or is that provided someplace else?
Yeah, no, that's exactly right. So I'll come to that bit in a moment, and then I'll show you how it works. Okay. I'm also conscious you asked a question that led into this, which was why we started the demo, which was around the data versioning. And so I just I'll pause for a moment and show you that every time a run is captured, that actually corresponds to a lightweight file system snapshot that's happening under the hood. And we use a file system called ZFS, which makes those snapshots instantaneous. You can take them in less than a second. And it also means that only the differences from one snapshot to the next need to be recorded and transmitted around, which means, for example, that if there was some bulky data in here and then the next run added these test, train, and validation files, only the exact blocks on disk that have changed from one run to the next need to be captured. And that technology is really what makes data reproducibility feasible. Yeah, I kind of answered the question you asked 10 minutes ago.
Okay. And now this is maybe getting way deep into the weeds, but does ZFS operate in user space? Like, can you deploy Dotscience out to, regular Linux machines and you have ZFS running within user space, or do you have to like run Linux on ZFS or something like that?
So ZFS is a kernel module and it runs as a Linux file system. Not everyone knows this, but ZFS has been available out of the box on Ubuntu since I think 1604. So if you're running Ubuntu, then you already have it. It's already there. You can just load it into the kernel. And Dotscience will also automatically install ZFS for you on Red Hat and a couple of other distros. Docker, for example, the Docker for Windows, Docker for Mac distro. They will all also just work out of the box.
So you're just mounting some ZFS file system. You don't have to be running on a ZFS.
Correct. Yeah, from the user's perspective, they don't have to do anything special. If you're really interested in seeing what's actually going on in this container, so this Jupyter is running inside a Docker container on the runner, and you can see that this .mesh file system. .mesh is the project that we created initially, which is a wrapper around ZFS, basically. Okay. We call it kind of Git for data. That's exposed that ZFS file system as the home directory inside this Jupyter Lab container.
Got it. Okay, cool.
Great. So what we're going to do next is, I actually just want to point out what happened here while we were talking, which is that we trained this TensorFlow model using the SGD optimizer and just for one epoch. And then we tested it against the test set. And it's got an accuracy score of 61%. So it's not a very good road sign classifier. I wouldn't want to be sitting in an autonomous vehicle that's driving around with this thing on board. But never mind. Let's just say I'm not a very good machine learning engineer. I don't really know my way around TensorFlow. So I'm going to have to ask someone for some help to make my model better. Just while I do that, I'll just also mention what I just ran here is there's a command to publish this TensorFlow model with this ds.model command. And what ds.model says is, hey, Dotscience, this is a model. And this is where Dotscience starts to specialize to things like to the different machine learning frameworks. Everything we've done before this is generic, basically processes with input files and output files and keeping track of those. But now we're saying, hey, Dotscience, this is a TensorFlow model. And we actually pass in the TensorFlow module as the first argument. And Dotscience figures out from that exactly which version of TensorFlow was used. And then it builds an appropriate TensorFlow serving Docker container. And then we do ds.publish, which says, hey, we trained this TensorFlow model. So now let's go and look at the run, which is this model run. And let's look at this run in a little bit more detail, because this is starting to get interesting now. We can see we have this piece of code that ingested the sign names CSV file. We also have the code which downloaded these three data sets, and those all went into this code which trained this model. And the model, the code which trained the model, then created these four files, the classes file, and then the various TensorFlow model files. And it also kept track of which parameters we used, the epochs, and which optimizer, and what accuracy score we got. So at this point, it's also worth pointing out that we've got this Explore tab for Metric Explorer. And so it's possible to say, well, this run at this time by this user got this accuracy score. And obviously this plot becomes more interesting when there's more than one model. So at this point, I throw my hands up and say, I'm not very good at TensorFlow. I need to bring in an expert. And fortunately, one of my colleagues is an expert at this stuff, and his name is Fred. So I'm going to add Fred as a collaborator. And then as soon as Fred has been added as a collaborator, he can log into Dotscience, and then he can start to take a look. And so Fred comes in, and he can take a look at the run. And because he's an expert, he can take a look and say, okay, well, I can see that you trained this model with this data set, fine, and so on. But he can also say, oh, look, these parameters, that's not very good. So he can leave a comment for me, and he can say, parameters look dodgy. Let me have a go at improving it. I'll fork it and make a PR for you. And then, of course, from my perspective, I can go in and I should be able to see the comments on this run. And we're going to plug this all into Slack so that everything's collaborative and people can get notifications of these comments. But even without my permission, because I've added Fred as a collaborator, Fred can do some asynchronous collaboration with me. And so he's gone and created a fork. And now his fork has got exactly the same set of runs in it that mine has. But the interesting thing is that Fred can now kick off a separate Jupyter instance that is, it's separate from mine. Like, we're not going to tread on each other's toes. It's actually running on a separate VM in a separate container. But we're both able to carry on doing work and make progress on improving the model in parallel. Now, if we had more time in this demo, I would show you how I can go and make some changes, and then Fred can kind of merge from master, in a sense, to or merge merge the changes from the upstream. But because we don't have a great deal of time, I'm just going to do kind of the simple case where I haven't made any changes and Fred makes a proposal.
The last point you made, the merge, that's within the context of the notebook?
Exactly. So we've done notebook diffing and merging as part of Dotscience. So we'll be able to see that in a minute. But yeah, for the sake of argument, like this is Fred knowing what he's doing. He's going to change the optimizer from the SGD optimizer to the Adam optimizer, and he's going to bump the number of epochs up to 3. So I'm then going to leave this running because it'll take a little bit longer to for this model to train at 3 epochs. And then I'm going to go back to Luke's world, and then I'm going to say, well, okay, we've got a model. It might not be the best model in the world, but let's deploy it. Let's deploy it to a Kubernetes cluster and then monitor the behavior of that model in production. So the way I can do that is I can go to the Models tab, and because that model was declared in Dotscience using ds.model, I'm now able to build that model into a Docker image. And so I can click this button and notice that I didn't have to think about Docker versions of things. I didn't have to think about TensorFlow serving or which port the container is going to run on, or any of that complexity. I'm able to just click a button, and Dotscience will automatically build a Docker image out of the versioned model that existed in my Jupyter notebook.
Now that's great if I'm the data scientist, but if I'm the ML engineer, DevOps person, might want a bit more control over what goes in that container. Is that something that is accessible to me?
So that would be a great feature request. We don't do that at the moment, but yeah, we currently use some kind of pre-baked Docker files here, but yeah, I think it would be totally reasonable to have the ability to configure the specific Docker file that you use and the image that you create to add any additional dependencies. So yeah, that's something we may well add in the future.
Okay.
Cool. So we've got this road signs model now, and
you've got the model. Status is complete. You can now deploy it.
Yeah. So let's ship it. Let's put this thing into production. So I'm now going to choose a deployer, and a deployer basically is a Kubernetes cluster. So you can attach multiple Kubernetes clusters to your Dotscience account. And by the way, you can deploy Dotscience on-prem or in your own cloud VPC, or use our SaaS version. So we have flexible deployment options. And then you can attach however many Kubernetes clusters you want to Dotscience by just running a single kubectl command to connect the cluster to Dotscience. So here we have a...
Dotscience doesn't, own, abstract, or kind of manage the cluster for me. You're assuming that that's there and someone's taking care of it and you're just using it.
That's correct. And we can, for clients that need support in standing up and operating a Kubernetes cluster, we can help them with that. It's also now easy to get a managed Kubernetes cluster from all of the big cloud providers. So we're kind of assuming that Kubernetes is becoming a commodity, basically. So I'm now going to deploy this road signs demo to this cluster, and I'm going to call it road signs, which is not the most imaginative name, but I can choose which Kubernetes namespace to deploy it to. I can scale the model up to more than one replica if I want to, and then I can hit deploy.
Mm-hmm.
And so I left it all at just the defaults. And you can see that this is going to automatically deploy that model to a REST endpoint in that Kubernetes cluster. And it's also going to wrap that model up with what we call the model proxy. And the model proxy is a sidecar that we created. If people aren't familiar with what that is, it's another container that sits next to the main container in a Kubernetes pod. And it allows the container to, it allows requests to go through the model proxy to the deployment. And in doing so, we're keeping track of the requests and the responses. And that allows us to do what we call statistical monitoring. So this will deploy to the Kubernetes cluster. And then we will be able to monitor that cluster. While that's deploying, let's go back to the model that Fred created, and we can kind of interleave the different pieces of the demo here. And we can see, well, okay, by training it with the Adam optimizer and 3 epochs, we actually got a much better accuracy score. So this model has now been published, and the version with 3 epochs and the Adam optimizer is now listed in the Dotscience runs. We can see this here as well. This is definitely an improvement, I think, in the terms of the accuracy score. We can now, Fred can now propose this change back to Luke. And so he can say, let's make a pull request. The pull request shows the diff going from the SGD optimizer up to the Adam optimizer and going from 1 epoch to 3 epochs. Fred can go ahead and make that pull request in the way that you're familiar with from GitHub. So Fred might say improving accuracy, try training for more epochs, and using Adam optimizer is better in my experience. And then Fred has gone ahead and opened that pull request. So if I go back to the model, for example, then sorry, to the project, then I can go and look at my pull requests, and I can see this improving accuracy pull request is open. And so I can say, okay, looks good. And I can go and review the diff. I can say, okay, well, those are the things that have changed. I'll make that comment, and then I can accept the pull request. So just before I do that, I have to stop my local copy of Jupyter so that Jupyter and the merge algorithm don't tread on each other's toes. And then I can go ahead and merge this in.
Cool. Can we, I don't know if the model's completed the deploy, but can we get a quick look at that, the monitoring side of things before we wrap up?
Yeah, totally. So let me just see. Okay, so the model is up and running. That error message is actually normal because you're meant to send post requests to the model, not GET requests. Yeah. So let's try monitoring the model. This is going to take us into Grafana. So what we do is we automatically create Grafana dashboards for each of the models that are running in the Kubernetes cluster. And you can go in and you can edit the PromQL if you want to, but you don't have to understand PromQL in order to use Dotscience. And so you can see right now there are no requests. Go ahead.
The kind of monitoring we're talking about here is monitoring of it looks like monitoring of the microservice transaction rates and latencies, as opposed to statistical monitoring of my decision service.
Well, actually, it's both. So let's send some requests to this model. So I've got a little app here that it is able to send road signs requests to models, and we can start hitting up this model that we're running in production. And I told you it wasn't very good. It thinks that this 60 sign is right of way at the next intersection. And it thinks that this it got no entry right. Let's see, it really likes right of way at the next intersection. This is kind of a classic, like, not trained enough neural net here. Okay, so it gets a stop sign right, and manages to do yield. But yeah, that's pretty bad. I wouldn't want a model running in my autonomous vehicle that can't figure out what the speed limit is. So we can go and have a look at what's actually going on here. And what we can see here is, I'll send it a few more requests just to make the graph look a bit more interesting. But yeah, as we send requests into this model, we're able to visualize and monitor the statistical distribution of the different categories that the model is categorizing. And so we can see here that even though we clicked on these buttons sort of equally, we've got a spike in the number of right of way at the next intersection predictions that are happening here. And probably see that a bit more clearly if I zoom in. And so using this statistical monitoring technique, you can set up tolerances, and you can set up, using the Prometheus Alert Manager, you can set up alerts to actually page a human, page a data scientist, if the model in production is misbehaving or behaving outside of the normal bounds that you would expect. And so one example would be that you might expect there to be a certain proportion of road signs that are classified in production would be stop signs. And if the number of stop signs that you're classifying in production drops below the expected threshold, or even if it drops to 0, then something changed. Either we deployed a bad model, or something changed about the world, and it turns out that these road sign classifiers, that the model that we trained isn't capable of classifying stop signs in the snow, for example. Like, stranger things have happened with machine learning models. So yeah, that's the statistical monitoring side of it. And I guess just to sort of finish the demo here, what we can see is that this model that Fred contributed, we can now go ahead and build that model into a Docker image. And that you can see here that the accuracy has jumped from 61% up to 86%. And so what we should be able to do quite easily is deploy that model to the Kubernetes cluster and then observe that in actual real world testing, i.e. that this application that we built here, that the model is able to do a better job of classifying that 60 sign. So I'm going to make a new deployment. I'll just call it road signs 2 because
I saw one of the options there was replace existing deployment. Does that stand up your model behind an existing endpoint so you can update it without, while it's running? Live update? Yes,
exactly. Okay. Yeah, and we're going to soon add the ability to have named deployments. So you see at the moment, every endpoint is just a random URL. But we're going to add the ability to name them, and then you'll be able to have like production as a name for your deployment and staging as a name for your deployment, and that's going to be pretty useful.
Anything fancy like canary deployments or things like that?
That's on the roadmap. Like once you've got more than one model, you definitely want to be able to test them against each other in the real world. So yeah, canaries and AB is definitely on the roadmap.
Okay.
So yeah, let's try out this other model. This is the new one we created, that Fred created. Oh, and it's better. It's not perfect, but at least it recognized it's a speed limit sign. So I'm going to call that a win. And yeah, unless there's any other questions, I guess that's kind of the end of the demo.
Awesome. Very cool. Very cool. Yeah, I think we covered a lot of interesting ground here. Any kind of parting thoughts from your perspective? I guess, one of that original question that led us into the demo was around the kind of what enabled the provenance and the things you're doing on the data side. And it sounds like that's the capabilities you built on top of ZFS. Would you say that that's kind of one of the core differentiators of what you're doing, beyond the user experience that you put together?
Yeah, totally. I think what we're finding is that, number one, companies need to get models into production and monitor them. Yep. And if you can't get a model into production and then monitor it and tell what it's doing when it's running, then you can't get business value out of AI and machine learning. So that's kind of like level one of your hierarchy of needs as an AI team inside an enterprise. But then once you've got models in production, and especially once you start getting more models into production and new versions of models into production, then if you haven't laid the groundwork for keeping track of your metrics and your hyperparameters, let alone keeping track of which versions of data you're using as input data. And if you don't have that reproducibility, so that if a model is running 9 months later and suddenly some stakeholder flags that an issue with the model and you need to go back and check for bias, for example, in the training data, then you're going to have a bad time. So it's both the sort of enabling the essential value from AI with deployment and monitoring, but then also keeping track of things, improving collaboration, and having that audit trail for the lineage, the provenance of the model, along with exact versions of which data went into each model, and doing that all in a controlled, collaborative and productive environment. That's how I'd summarize it.
Awesome. Are you or anyone else on the team going to be out at KubeCon next week?
Yes, my colleague Chris will be at KubeCon. We don't have a booth at KubeCon, unfortunately, but if you tweet me,
I suspect that
twitter.com/lmarsden.
I suspect KubeCon will be passed by the time this is published, but I'll be on the lookout for Chris.
Yeah, you should definitely meet up with him. And then I'm also going to be at reInvent in December. So and we will be exhibiting there. So yeah, come and check us out.
Awesome. Well, Luke, thanks so much for being a guinea pig and working with me on this experiment. I think it was great. For those of you out in the viewing/listening audience, definitely reach out and let me know what you think about this demo.
Awesome. Thanks so much, Sam.
Thanks so much.
Really appreciate it.
Bye.
Cheers. Bye.